Hello there, welcome to my channel on chemistry lessons. Predominantly it focuses on AQA A-level, but it also covers the BTEC applied science specification as well. So most of the videos are designed to be as interactive as possible, whereas it'll be kind of a lesson to follow through. So there'll be information and there'll be sections of the video where you're asked to pause and answer questions, and then obviously you can unpause the videos and go through and hear the answers. So this video then, it's lesson 1 in a series of 3, and it covers the beginning of your organic chemistry. It's the 3.3.2 alkanes topic, and it's AQA chemistry. So this one's lesson 1 of 3, and it covers the properties of alkanes. So this is the spec points then. I always say that when you're learning something or you're revising, either way, always have the specification in front of you. It seems obvious, but you've got to make sure you focus on the things you're supposed to know for the exam. So the mistake at this topic is to assume that you already know it, because you actually have talked about fractional distillation of crude oil at GCSE, and you'll have also probably talked about cracking. However, we need to be able to talk about cracking particularly in more detail, and when it comes to fractional distillation, we certainly know an awful lot more about intermolecular forces. Okay, so don't be fooled into thinking you already know it. You don't. Okay, so make sure you spend some time on this. Right, okay, so boiling point then. So this is alkanes. Let's think about what alkanes are. They are hydrocarbons. They consist of only carbon and hydrogen atoms, and we have single bonds between all of the carbons. Now, in terms of boiling point, what types of forces are we going to find between a hydrocarbon? Now, a hydrocarbon, we've said it consists of only carbon and hydrogen, and these bonds are considered to be non-polar. So these bonds are non-polar. Therefore, molecules of hydrocarbons are non-polar molecules, which means you do not have dipole-dipole bonds between molecules. The only intermolecular force we're going to find here is going to be van der Waals. So as a result, alkanes have relatively low boiling points because they only have weak van der Waals forces between molecules. And be prepared to discuss or talk about what van der Waals are. So that's in earlier topics of bonding, be able to talk about how a van der Waals force arises. Now, in terms of the trend in the boiling point, as the chains get longer, the boiling point increases, and that's because the molecules are bigger, they have more electrons. The more electrons you've got, the stronger the van der Waals, and therefore the higher the boiling point. Okay, something to mention here though, if we were to consider something that has a straight chain, so 1, 2, 3, 4, 5, 6 carbons long, or if I had something that 1, 2, 3, 4, 5, 6, this would be classed as a straight chain, and this is a branched isomer. Now the branched isomer actually has lower boiling point. So despite the fact that they do have the same amount of electrons, so they're going to have the same random movement, the fact that it's branched means that you're going to have less contact points. So the interactions with neighboring molecules will be weaker. You could visualize it as almost a surface area thing. You've got more contact points between straight chains than you do between branched, and therefore the boiling point of a straight chain is higher than the boiling point of a branched. So just be aware of that. In terms of solubility, solubility is talking about the ability it has to dissolve in water. Now, again, reminder, water is polar. It's a polar solvent. Okay, so it's a polar solvent, and therefore it dissolves polar molecules. Since alkanes are non-polar, alkanes are insoluble. So alkanes are insoluble in water, so they don't dissolve in water. Okay, so what we need to be able to do is we need to be able to talk about fractional distillation. We need to know what it is and how it works. Okay, so be prepared to answer that question. And we're then going to look at what cracking is and the economics importance. But here we have two different types of cracking, and we need to be specific in each case in terms of how the conditions are different and the likely products for each case. So this is where it's definitely different from GCSE. So fractional distillation then. What is fractional distillation? Well, it's separating a mixture. So first of all, fractional distillation, it's a technique to separate a mixture. Now, crude oil is a mixture. It's a mixture of hydrocarbons. So we've got lots and lots of different hydrocarbons of varying chain length. You can see that the chain lengths can vary from 1, which would be CH4, all the way up to long chain lengths above 70. So you've got quite a mixture there. And fractional distillation is used to separate out that mixture based upon the boiling point. You heat this substance up, and the chains that are shorter, they boil or evaporate first because they have weaker van der Waals. So we can talk about van der Waals forces here. So the shorter chains have weaker van der Waals and therefore lower boiling points, and they will move further up the column. So you find the shortest chains at the top and the longest chains at the bottom. Now, you do not need to know these temperatures, so do not feel the need to memorize temperatures. It's not needed, okay? So don't think about the temperatures. Likewise, the chain lengths are not needed. The order of the chain length, yes, you should be aware that the chain length gets longer. And I always advise that people should probably know some fractions in the order. So the easier one, gases come out the top, refinery gases. And I would probably pick 3 of the other ones to know, okay? And in the order of their length, but you don't need to memorize all of these. So don't feel the need to know all of these all the information here, but make sure you do know some of the names of the fractions in order. So maybe pick these 3 in order, for example, okay, and make a note of them. Okay, so following fractional distillation, the whole point of fractional distillation was to separate the mixture out so that we could sell those fractions for their particular uses. Now, each fraction has its use, and some of them are more popular. There's a high demand for some chains. Now, typically the shorter chains are more useful. So petrol up over, they're very useful, and therefore there's a very high demand for them. The longer chains, less useful, there's less of a demand. So cracking is a process used to take those longer, less useful chains. So let's just take an example here. Take a long chain that's not very useful. And cracking is taking that long chain and breaking it into several shorter chains. We also end up making alkenes in that process as well. Okay, and we'll talk about that in a moment. Now, at GCSE, you do cover cracking, but we need to cover it in a little bit more detail here because there's actually 2 types of cracking. Okay, there's cracking, there's thermal cracking, and there's catalytic cracking. You are expected to recognize the difference and know the difference in both. Now, as the name suggests, thermal cracking is done at a very high temperature, somewhere in the region of 1000 kelvins. It's also done at a very high temperature, somewhere in the region of 70 atmospheres. Now, whilst I'm not going to say you don't need to memorize these, it is worth knowing that it is a high temperature and high pressure. Okay. Now, this is done in a very short space of time, and what happens is your long chain is broken into short chains and quite a lot of alkenes. So this one produces alkene rich. So this makes quite a lot of alkenes. That's kind of your key recognition really when it comes to exam questions. If they're asking you what type of cracking do you think this is, you should be looking to see how many alkenes are formed. If it forms quite a lot of alkenes, so 4, 5, 6 different alkenes, then it was probably thermal cracking. If it doesn't produce many alkenes, it has to produce at least one, but if it only produces a very small number of alkenes, then it was probably catalytic. So let's have a look at what catalytic is. So funny enough, catalytic is still done at a fairly high temperature. Okay, so it's still done at a fairly high temperature, not quite as high. Okay, but noticeably the pressure is significantly smaller. Okay, the spec actually uses the term slight pressure. So the term slight pressure is often used, and that's because it's just above atmospheric. Atmospheric is 1, so it's slight pressure. And the catalyst used, though we do need to name the catalyst is zeolite. Okay. Now this one here, it doesn't make as many alkenes. So the key trigger really in the exam is to look out for the amount of alkenes made. And we'll look at some exam questions later on to kind of reinforce that idea. Okay, straight into some exam questions then. So what I want you to do is, hopefully you know the drill by now. You're going to pause the video, have a go at the question, and when you're ready to go through it, you can unpause the video. Right, let's have a look at this question then. So which statement is correct about fractional distillation? Zeolite catalyst. Well, I'm going to say no. I think that was cracking. Each fraction contains a mixture of hydrocarbons. Okay. Might be misleading, that one, we're not sure. Gaseous fractions are formed by breaking covalent bonds. No, when you're separating the mixture, you're not breaking any bonds within the chain. You're only breaking the bonds between the chains, which is breaking van der Waals forces. Cracking involves breaking covalent bonds, but fractional distillation only involves breaking intermolecular van der Waals forces. So I'm saying it's not C. The fractionating column is the hottest at the top. No, it's not. It's the lowest temperature at the top, the highest temperature at the bottom. Lowest temperature at the top with the shorter chains, higher temperature at the bottom with the longer chain. So that's incorrect. So the correct answer here is B. And I've used a little bit of, I suppose I've used process of elimination there, because each fraction does contain a slight mixture. So if you go back in the video, you'll see that diagram of the fractional distillation column, and you'll see that there's a very short range within them, but there's still a range, so you don't get exactly 5 carbons long from one fraction, then the next fraction exactly 6 carbons long. So it's not that precise. It separates them into fractions, which is like a range of lengths. Okay, and like I've said, you do not need to know those ranges. Okay, so next question. This question is in fact out of 8 and not 17 because I've removed some parts of the question to only focus on the topics in this video. So you know the drill, answer the question, and when you're ready, unpause the video and we will go through it. State the process used to separate an alkane from a mixture of alkanes. Well, the process used is fractional distillation. It does need to be fractional distillation as well, not just simple distillation, because there is a difference. So it must be fractional. Fractional is where we're going to have multiple parts of this. We're separating more than one thing. So fractional distillation is needed. B. So C3H8 and C4H10 can be liquefied as used as fuels for camping stoves. Suggest with a reason which of these fuels is liquefied more easily. It's basically asking you which one has the lowest boiling point. Okay, so which one has the highest boiling point, sorry, because you're going to cool them down. So these are both gases, you're going to cool them down, so which one has the highest boiling point, which one's going to be easiest to turn into a liquid? And I'm going to go with C4H10 because it has stronger van der Waals forces, or more van der Waals forces. Okay, so I'm picking C4H10. IUPAC name for X. Okay, so it looks quite confusing, but we've got to find the longest chain. Now, no matter which way we look at this, the longest chain is 3. So it's 3. It's propane. And this is, in fact, dimethyl propane. I don't need numbers here because the methyl groups can't be anywhere else. But if you've called it 2,2-dimethyl, the examiner won't hold it against you. So 2,2-dimethyl propane is acceptable, but really it should just be dimethyl propane. X has a boiling point of 9.5. Explain why the boiling point of X is lower than that of its straight chain isomer. Okay, now when we look at straight chain, now we don't know the size of X. It doesn't really matter. Okay, the fact is that X was branched or unbranched. So if it's straight chain, you could say it has a bigger surface area, more contact points, therefore more van der Waals or stronger van der Waals in the straight chain. And in the branched, it's going to have less contact points and therefore weaker van der Waals forces, which means it has a lower boiling point. Okay. And D, deduce the molecular formula of Z. So let's see how we're going to work this out. So we have one molecule of ethane. Ethane is C2H6. One molecule of propene. Propene is C3H6. And 2 molecules of ethene. Ethene C2H4. So let's just add up. How many C's must we have had? 1, 2, 3, 4, 5, 6, 7, 8, 9, because we had 2 of these. There was 2 ethenes, so that's 9 carbons. And how many hydrogens? 6 plus 6 plus 4 is C9H20. State the type of cracking that produces a high proportion of ethene and propene. Give 2 conditions. Right, so this is where we're asked for the 2 different types of cracking. Now, because we've made 1 propene and 2, so we've made 3 molecules of alkenes here and 1 molecule of alkane. So this is, I would call this alkene rich. Therefore, it must have been thermal cracking. So thermal cracking. What are my conditions here? High pressure and high temperature. I could quote the actual values, but I don't need to, okay? So it's high temperature and high pressure are accepted there. Okay, question number 3 then. So again, you know the drill. Pause the video, and when you're ready, unpause and we'll go through the questions. Okay, 3 marks then. So we're asked to meaning of the words saturated and hydrocarbon as applied to the term saturated hydrocarbon. So saturated means it only contains single bonds, 1 mark. Hydrocarbon consists of only hydrogen and carbon atoms. Okay, we must say only hydrogen and carbon. If we say that it contains hydrogen and carbon, that doesn't mean hydrocarbon. It only contains hydrogen and carbon. And finally, for the 3rd mark, the homologous series that C8H18 belongs to is alkanes. That belongs to the alkanes homologous series. Okay then, B. So outline the essential features of the fractional distillation of crude oil that enable crude oil to be separated into fractions. Now, 4 marks here. So the first thing I'm going to point out is that different fractions or different hydrocarbons or different lengths have different boiling points. There's my first mark. So I'm saying that they have different boiling points. Okay, and the boiling point depends on the size or the molecular mass or the size of the molecules. Okay, the bigger molecules have higher boiling points because they have more or stronger van der Waals. And then what we talk about the fractionating column now, we can say that the fractionating column has a temperature gradient or a range of temperatures where it's cooler at the top and hotter at the bottom. And the shorter molecules with the lowest boiling points will move further up the column. So small molecules are collected at the top of the fraction, and the larger molecules with the higher boiling points are collected at the bottom of the column. So all we're doing there is explaining the process of how fractional distillation works. And finally, part C then. C8H18 is obtained by the catalytic cracking of suitable heavy fractions, so that's basically heavy fractions of the long chains. State what's meant by the term cracking, so this is a vague one, and name the catalyst using catalytic cracking. Okay. So the term cracking is taking long, less useful chains and breaking them down to smaller, more useful chains. And the catalyst used is zeolite. Okay, so there's our first 2 marks. And then we're asked to write an equation to show 1 molecule of C14H30. It's cracked to form 1 molecule of C8H18 and 1 molecule of another hydrocarbon. So let's just work out what's left. What's left here is C6. There's 6 carbons left over, and there's 12 H's. So C6H12. That's an alkene. Okay, that's 1 alkene and 1 alkane. So it's not necessarily alkene rich there. So that would make sense about catalytic cracking. And why do they crack suitable heavy fractions? Well, that's simply because the smaller chains are in more demand than the longer chains, and therefore there's more use, there's more chance of selling them. So it's more profitable. Shorter chains are more profitable. Right, that's the end of that one then. So hopefully that was useful. Look out for the lesson 2 in alkanes, which is going to focus on combustion and pollutants to do with alkanes and burning of hydrocarbons. Good luck.